Qualitative means a quality, something's quality, like hair color or favorite class, something that's not a number. So the favorite color crayon of first graders will be qualitative. Discrete and continuous are both numbers. Discrete is a whole number. A good hint is to look for the word number of. So number of babies born each day at Memorial Hospital, or number of pair of shoes you own, or number of children you have. That's discrete. Continuous is something that could be not a whole number, so could have fractions or decimals. So length of time, the weight of something, the height of something, a measurement usually, that's continuous. Classify each of the following as nominal, ordinal, interval, or ratio. Start with nominal. I think nom is like name. It's the name of something, sort of like qualitative. Something that has no order is not usually a number. The hair color of students, that's nominal. Ordinal is something, usually names, where there is a first, second, third. Ordinal means the ordinal numbers, first, second, third. So where it's names, but they're in some kind of order. So that would be shoe sizes. They're still names, but we can put an order on them. AAA is smaller than AA, so on. Interval and ratio are both numbers. What I'm deciding between interval and ratio, I look for temperature. That's going to be your interval. Ages, that's a number, so ratio. Go to your book if you're interested in more definitions, more specific definitions on the differences between interval and ratio. Classical, empirical, or subjective. I usually start with subjective. That's the one where you're looking for an expert's opinion. So a geologist says there's a 30% chance, that's subjective. Empirical, I think of the E in empirical and put in the word experiment there. An experiment or a study. You're looking for an experiment or a study. So we've got a survey here. That is going to be empirical. Classical is when you're figuring out probabilities based on sample spaces. So a die is rolled, or the probability of drawing a jack. Figuring out probabilities based on what should happen. That's classical. Mutually exclusive. Mutually exclusive means the two events can't happen at the same time. I think of people that are in a relationship. If you're mutually exclusive, you can't have another girlfriend or boyfriend at the same time. So, draw a card. The card is a diamond, the card is a spade. Can those things happen at the same time? They cannot. They cannot happen at the same time, so they're mutually exclusive. Select a student in a science class. The student is male, the student has blue eyes. Those two things are happening at the same time. Somebody has two girlfriends. That's how I think of it. So they're not exclusive with their girlfriend. So not mutually exclusive. Rolling a die. Getting a number less than 4, that'd be a 1, a 2, or a 3. Getting an odd number, that'd be a 1, a 3, or a 5. Can those things happen at the same time? Yeah, you could get a 3 that would be happening at the same time. So they can't happen at the same time to be mutually exclusive, so this is not mutually exclusive. Determine which events are independent and which are dependent. In dependent events, the outcome of the first event affects the outcome of the second event. In independent, they don't. The first event does not affect the second event. Drawing a king, replacing the card, and drawing another king. If you replace the card, then the probability of drawing that second king stays the same. So these are independent. It doesn't change the outcome, the probability of the outcome of the second event. drawing a king, not replacing the card, and drawing another king. If we're not replacing the card, now the probability of drawing the second king is changed, and so therefore those are dependent. This one you could maybe argue with me. Sitting in the last row in a classroom, getting an A in a class. I would argue that those two events do not have an effect on each other, therefore independent. This next question I'm sure that you'll see on your final in one form or another. Which of the following cannot be considered a probability outcome? Probabilities all go from 0 to 1, including 0 and 1, or 0% to 100%. So probabilities can be decimals as long as they're between 0 and 1, and they can be fractions as long as they're between 0 and 1, and they can be 0 and they can be 1. So what probabilities can't be is numbers that are greater than 1. They also can't be negative numbers. They can't be less than 0. So we're looking at this one right here. This is greater than 1 or greater than 100%. That is not a probability outcome. Neither would a number that's bigger than 1, neither would be a negative number. Let's look at 7, 8, and 9. These three problems can all be done easily on the calculator. But let's go over our counting rules and which thing you would use when. Let's do an example. Let's say you have 5 items and 3 spots to put them in. First question you ask is, are there any repeats? Are repeats allowed? If they are, then you would do 5 to the 3rd power. Or it's like saying, here's the 3 spots. How many choices for the first spot? 5. How many choices for the second spot? 5. How many choices for the third spot? 5. Okay. Let's say you can't have repeats. Then you have to ask yourself, does order matter? If order matters, yes, then you would do 5p3. Or, again, put your spots out. How many choices for that first spot? 5. How many choices for the second spot? 4. How many choices for the third spot? 3. 5p3 is the same as 5 times 4 times 3. If order doesn't matter, then you do 5c3. It's a little more complicated to do this. You'd actually have to divide out some of these. This is going to be a smaller number if order doesn't matter. So then what's this right here? 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. So that would be an arrangement where repetitions are not allowed, order matters, but instead of having 3 spots, you have 5 spots to put them in. That's when you'd use the factorial. The 5 factorial is also equal to 5p5. A little review on that. For the class limits of a class that goes from 8 to 18. When I think about this problem, I have to think of it actually as a distribution. So my class limits, so I would think of this like people's ages. Maybe, so one class goes from 8 to 18, then the next class 19 to 29, then the next from 30 to 40, and so on. So I'm just looking at this class right here, the one that goes from 8 to 18. What would the boundaries be for that class? 0.5 below to 0.5 above. Those would be the boundaries. What's the class width? If you look in your formula sheet, it'll tell you it's the upper boundary minus the lower boundary. Not the limit, upper limit minus the lower limit, mind you. So I do 18.5 minus 7.5 and I get 11. Another place to see the class width is from the beginning of one class to the beginning of the next class. From 8 to 19, that's 11. That's another way to do class width. Find the class midpoint. On your formula sheet, it'll tell you to take the lower boundary plus the upper boundary and divide by 2. So that'd be 7.5 to 18.5, so add those two and divide by 2. It also works for the midpoint. You can use the class limits on this. If you add 8 plus 18 and divide by 2, you'll get the same answer. That class midpoint, XM, is the symbol for it, is 13. Let's look at 13 and 14 together. The average age of a resident of Honolulu is 77, so that's our mean. Same thing in 14. With a standard deviation of 4.5, so that's our standard deviation. What is the z-score of an 85-year-old woman? So we're looking for the z-score, so that 85 is our data value. Down here, we have the z-score, and we're looking for a data value. So you need to go to your formulas and find the right formula to use. Here's the formula for finding the z-score when you have the data value. So plug your numbers in. And you'll come up with the answer 1.78. That's a z-score. It looks like a good z-score. It should be positive since my data value is above the mean, so I'm not surprised there. 14, this is the formula for finding the data value when you have the z-score. So plug your numbers in. $71.6. That's the age of the man with a z-score of negative 1.2, and that doesn't surprise me either. My z-score is negative. I should be below the mean. The mean's 77. I'm below 77. When you're using your standard normal curve sheet, remember that the numbers on the outsides are your z-scores, and the numbers on the insides are your probabilities. The numbers on the outsides can be positive or negative. Z-scores are positive or negative. But the probabilities are all positive. They are all between 0 and 1, just like probabilities are. 15, to the left of negative 2.06. That should be labeled as a z-score of negative 2.06. So that's right about here. And I want to the left of that. Our table always gives probability that you're to the left of it. So all I have to do is look up that z-score on the outside and find the probability on the inside. Number 16, the probability that your z-score is between negative 1.89 and 0. So this shaded spot. Go to your table, look up a z-score of negative 1.89. You find that the area to the left of it is 0.0294, and the area to the left of 0 is 0.5. Subtract those two and come up with 0.4706, 47.06%. That's the likelihood that you're in this shaded area. 17. Let's talk about what this statement right here says. The probability that your z-score is between negative 2.32 and 1. So negative 2.32 about there and 1 about there. So I'm looking for the probability of being in this shaded region. Go to your z-score table and look up the probability of being to the left of 1, 0.8413, and the probability of being to the left of negative 2.32, which is 0.0102. Subtract those two, 0.8311, and that's the probability that you are in the shaded region. Number 18 is similar. The probability that you're between a z-score of 1.8 and 2.39. Look up your probabilities on the table, take the bigger one minus the smaller one, and that will give you the area between the two z-scores. What does this say? The probability that z is less than 2.01. So 2.01 and the probability less than. Again, our table shows less than. So all I have to do is look up the z-score of 2.01 on the outside and find the probability that I am to the left of that z-score. The probability will be in the inside of the table. 0.9778. I'm going to add a problem, 19b, I'll call it, because there isn't one like this. I want you to also think about what's the probability that the z-score is greater than 2.01. So greater than 2.01 over here. Well, our table shows the probability that you're to the left of that. So how do we find when you want to the right, the greater than? We know that the whole area under the curve is 1. So if we know that to the left is 0.9778, to find the probability that you're to the right, you just take 1 minus that. So the probability that the z-score is to the right of 2.01, greater than 2.01, is 0.0222. There are two ways to do the binomial distribution. One way is to use this formula found on your formula sheet, or you can use the table in the back of the book called binomial distribution. What is the probability of getting 3 questions correct on a 10-question multiple choice quiz? There are 5 choices for each question. So n is the total number of questions, or total number of trials, 10. X is the amount of successes you're looking for. So here we're looking to get 3 questions correct, so that would be a 3, exactly 3. P, the probability of success on one event. So there are 5 choices per each question. So if you're going to guess one right, what's the probability of doing that? 1 out of 5, 1/5, or I use the decimal form of that, 0.2. Q is then the complement of P, 0.8. Or the probability of failure. So if there are 5 choices per question, 1 choice is right, what's the probability of being wrong? 4 out of 5, or 0.8. After you find N, X, P, and Q, it's simply a calculator problem. So this is the probability of getting exactly 3 questions correct. If it said at least 3, you'd have to figure out 3, 4, 5, 6, 7, 8, 9, 10 and add them all together. If it said more than 8, you'd have to figure out X is 9, X is 10 and add them together. But this is the probability of getting exactly 3 questions right. Find the mean. My first step is to order all of my data values. I always count up my number of data values and make sure I have the same number in my list so that I didn't forget anything. The mean. The formula for finding mean is sum of the data values divide by n, divide by how many you have. So we need to add up our data values. So we'll take 61 and divide by the total number that we have. The mean is 7.6. Mode. Mode means most often. Our most often occurring data value is 8. Median means our middle value. I start counting towards the middle. I actually have 2 middle numbers. Now they're both 8, so our median is going to be 8. But let's say they were different. I'd add them up. 16 and divide by 2. My median is 8. If you don't have 2 middle numbers, if there's just 1 middle number, that's your median. Standard deviation or variance. I'll do standard deviation. The formula is right here. To do that, I need to know n, which is the number, which is 8. Sum of the x squareds. To do sum of the x squareds, I need to make a column for the x squared terms. Then I'll sum them, add them up, and that'll be the sum of the x squareds. So my standard deviation will be square root of n is 8, sum of the x squareds, 483, minus sum of the x's squared, so that's 61 squared, over n times n minus 1. I'll evaluate that. I get 1.6. Range. Range is high value minus low value. Range is 5. Sum of the x's is 61. Sum of the x squareds. That means I square all the data values and then add them up. 483. This means sum the x's first, get 61, and then square that answer. I'll do the box plot. To do the box plot, you need to have the 5-number summary, which is your low value. Our low value is 5. Our high value, 10. Our median value, 8. And then we need Q1 and Q3. So let's see, our middle was right here. So what's the median of the bottom half? That'll be Q1, split it into 4 quarters. So our middle is actually 2 middle numbers here, 6 and 7. So I add them and divide by 2 and I get 6.5. And Q3 is the median of the top half. There's 2 middle numbers in the top half. So again, I add them up and divide by 2 and I get 8.5. There's my 5-number summary. Now I'll show that in a box plot. First, I make a number line. Then I make a box that goes from Q1 to Q3. Then I make a line for the median. Then I put a whisker up to the high value, down to the low value. Then I write in the data values above each of the 5-number summary points, and that is my box plot. To calculate the class width for 4 classes, class width is the range divided by the number of classes. Our range was 5, and the number of classes that we're told to use is 4. That's 1.25. And whenever you're finding class width this way, you always round up, even if convention would tell you to round down, and you'd use 2. First of all, what is a probability distribution? It's a list of all the possible outcomes, and then the probability each could happen. So let's say this was one time we did one about how many fish a guy catches. So here's all the total possibilities. You could get somebody catches 0 fish, that's a probability of 0.2. They catch 1 fish, a probability of 0.3. They catch 2 fish, a probability of 0.15, and so on. The sum of the probabilities in a probability distribution should always add up to 1. So how do you find the mean, variance, and standard deviation? A common mistake, people will try to use the standard deviation and mean from chapter 3 in their formula sheet. You actually want to look at chapter 5 when you're finding the mean, variance, and standard deviation of a probability distribution. And you'll find it says mean for a probability distribution. Mu equals sum of x times px. And variance, it'll tell you, is this. Oops. The mu is the mean. Standard deviation is just the square root of that stuff. So now I have to figure out what all this stuff is. So you see over here in this chart, I've rewritten the probability distribution vertically so that it's easier for me to make myself an XPX column where I just times the X times the PX and write it there all the way down, and an X squared PX column where I take the X value, square it, and times it by the probability distribution, or by the probability. So I'll fill out the rest of my chart. Once I've filled out the rest of my chart, I can find the sum of the XPXs and the sum of the X squared PXs. Now that I have that information, I can figure out my mean. The mean is just the sum of the XPXs. We already figured that out, 1.7. I made a mistake when initially writing down my formula. There should be a squared here and a squared here. So when I find my variance, I'll take the sum of the X squared PXs. I've already found that, 4.4. And I'll subtract mu, my mean, 1.7 squared, which is 1.51. Then my standard deviation, I just take the square root of that number, or again, the square root of the same thing, the sum of the X squared PXs, 4.4, minus mu squared, 1.7 squared, or the square root of 1.51, which is 1.23 about. So standard deviation, variance, mean. Again, the biggest mistake is not knowing where to find the formula. You have to look under Chapter 5, under the probability distribution part. Using a tree diagram. We'll start with urn 1 to see what could happen first. So urn 1 has 3 red and 5 blue marbles, so what's the probability of getting a red? 3 out of the total of 8. What's the probability of getting a blue? 5 out of the total of 8. So then let's add in urn 2. So after we choose that red ball, what's the probability of getting an orange or a green? There's 4 of each, so the probability of getting an orange is half, and green is half. Same thing down here. After we get the blue, then the probability of getting an orange is a half, and green is 1/2. So then let's figure each of these out. The probability of getting a red and then an orange. Remember, when you say and then, you multiply probabilities. So 3/8 times 1/2 is 3/16. So the probability of getting red and then an orange is 3/16. 3/8 times 1/2, red and green, again 3/16. Blue and then orange, 5/8 times 1/2, 5/16. Blue and then green, 5/16. Notice that if you add all these together, they will sum to be 100%. All of the probabilities added together. So, B. What's the probability of getting a red and then an orange? We already figured it out, 3/16. What's the probability of getting a red or an orange? So that means you could get a red, or you could get an orange, or you could get both. So which things is that? Okay, so red is here and orange is here And here, but we already counted that one. So we've got 3/16 plus 3/16 plus 5/16. So that's 11/16 is the probability of getting a red or an orange. Counting techniques. Using the digits 1 through 6. So that means there's 6 choices for numbers. How many different 3-digit numbers can be made? So that means 3 spots we're putting them into. So if repetitions are allowed, that means for each of our 3 spots, you have 6 choices for the first spot. You can repeat, so you've got 6 choices for the second spot and 6 choices for the third spot. So that's 6 to the third power. So if repeats are allowed, multiplication rule, 6 times 6 times 6. So that's 216 choices. If repeats are not allowed, then you have to ask yourself, does order matter? If it does, so no repeats and order matters, then you want to use P. 6, P, 3. Number of choices, P, number of spots. Or another way of thinking of that is you have 3 spots. How many choices for the first spot? 6. You can't repeat, so now there's only 5 choices for the fifth and 5 choices for the second and 4 choices for the third. So either way, that is 120 choices. 120 choices there. If order doesn't matter, then you want to use combinations. 6C3. Find the expected value of a game that costs $1 to play. Player rolls a fair die and receives the number of dollars equal to the number of dots shown on the face of the die. How much should the player expect to win for each play? I make myself a probability distribution. Under X, I put the net gain. On the side, I like to put a little cheat sheet, like what will happen. Well, if I get a 1, what's my net gain? Well, I win $1, but I paid $1 to play, so my net gain is 0. If I get a 2, I get $2, but it cost me $1 to play, so my net gain is 1. If I get a 3, I get $3 minus the 1 for the $1 to play, and so on. P of X, the probability of each of these things happening. Well, it's a fair die, so the probability is going to be 1/6 for each choice. So then I go to chapter 5 and I look up my formulas and I find the formula for expected value expectation. And it tells me that expected value is the sum of XPX. So I need to make myself an X times PX column. I'll evaluate each of these and then add them up. And this right here will be my expected value. So I did X times PX for each row of my column. And now I'm going to add up all these numbers and I get 5/2, or 2.5. I did this a little bit differently than was done on the key. So 2.5, $2.50 is the expected value. That means on average, if you played the game long enough, on average, you'd make $2.50 for each play, on average. The average age of a worker at the average wage of workers at a fast food restaurant, so the mean is $5.85. Standard deviation, assume it's normally distributed. If a worker is selected at random, so one worker, not the mean of a bunch of workers, what's the probability that the worker earns less than $5.50? So I wrote it out as a probability statement. The probability that the data value is less than $5.50 an hour. We've got to change that data value into a z-score. So we use the z-score formula, and we get -1. So that means that this data value, if the x of being $5.50 goes with a z-score of -1, Now we need to find the probability that we're to the left of that. What's the probability they earn less than that z-score of -1? So to the left of is what our table shows. So we just look up a z-score of -1 and we find that probability. The probability that you're to the left of a z-score of -1 is about 16%, 0.1587. Same original data of mu, sigma. So now I want to know if one worker is selected at random, what's the probability that their wages are between 550 and 620? So what's the probability that the data values are between 550 and 620? First thing we have to do is standardize this, change it into z-scores. So we use the same formula up here to change 550 into a z-score, which we already did. That's negative, so that z-score is -1. And 620, so 6.2 minus mu divided by standard deviation, we find that that z-score is 1. So we're looking for z-scores between -1 and 1. What's the probability that we fall in that area? So we look up the probabilities for -1 and 1. That's the probability that we're to the left of these z-scores. And then we subtract them to find the probability that we're in between those two values. So 0.8413 minus 0.1587. About 68%, the probability that you're going to be in this area between those two z-scores, between those two data values. At a nursing school, it gives you the average score on an entrance exam, the standard deviation, and tells you that the school only wants the top 15%. So 15%, that's a probability, 0.1500. So they want the top 15%. I don't know exactly where it's going to be, so I'm going to kind of guess somewhere in here. The top 15%. 0.1500. Now we're going to try to use our table, but remember our table always measures to the left of the z-score. So actually our table is going to tell us this value right here. But luckily we can figure that out. We know that all the area is 1 or 100%. So if we subtract off that 0.1500, 15%, we'll get 85% is left, 0.8500. So we're looking for the z-score that has 0.8500 to the left of it. So we go to our table and we look in the middle of it. We look in the middle of the numbers at the probabilities. And we look for a probability that's closest to that. And then we look on the side and look for the z-score that corresponds with that. And so when you look for that, you find that the z-score that corresponds most closely with a probability of 0.5800 is a z-score of 1.04. So this right here is 1.04. That's our z-score. Now that doesn't really help us much because we want a data value. We want the cutoff score, what I have to get on the test to get in that top 15%. So then we use our formula, which changes a z-score into a data value. The data value is the z-score times the standard deviation plus the mean. So I plug my numbers in, my z-score, my standard deviation, and my mean, and I get 158.6-ish. And that kind of makes sense. There was my average score, and I have to get this score to be in the top 15%. That's the lowest I can get to be in the top 15%. Determine the correlation coefficient. That's the R value. The easiest way to do this is to put in your X values and Y values into your calculator under two variable stats, then compute the statistics and find the R. You can also use the long version, which uses a formula from chapter 10, and you have to use the sum of the xy's, sum of the x's, sum of the y's, the n, throw it into a big formula. Much easier to do it with technology. Find the equation of the regression line. Again, you go to your calculator and you look for the A number and the B number. Now, this is not the equation to your line. You have to put that into your equation. So that'll be y equals ax plus b. So our a is 0.738 times x plus the b number. That is your answer. The equation of the regression line or the equation of the line of fit. Use the regression line to predict y when x equals 50. What this equation says in words is y is 0.738 times the x value minus 0.144. So if you want to know what the y will be when x is 50, you just do 0.738 times 50 minus 0.144. Your calculator will also tell you all of these things. I've filled in the sum of the x's, the sum of the y's, the sum of the xy's, the sum of the x squareds, and the sum of the y squareds. To get these two values, you need to do a little bit more work. Sum of the x squareds with the sum of the x's in parentheses means you find the sum of the x's first, then you square it. So we know that the sum of the x's is 358, so we do 358 squared. And similarly for sum of the y squareds. You find the sum of the y's first, 263, and then you square that value. You can also do this by hand. You would write this data vertically, so you'd have a column for the x's, and then a column for the y's, and then a column for the x squareds, a column for the y squareds, and a column for the xy's. To get x squared, you just take all the x values and square them. To get the x times the y, you just take the x values times the y values and make a column out of that. When you're done, you would sum all of these columns, and you're going to end up with these values. Probabilities range from 0 to 1, or 0% to 100%. You can't have negative probabilities. You can have probabilities greater than 1. Probability of x is 0 means that event x will not happen. 0% chance. Probability of x equals 1 means that event x will certainly happen, or 100% likely to happen. Correlation coefficients, the R values, range from -1 to 1. R of -1 means that there's a negative relationship between x and y. As the x goes up, the y goes down. That it's -1 means that your data values fall directly on the line of best fit. As your numbers get further from -1 and closer to 0, that means that your data values are more spread out. An R value of 1 means a strong positive correlation. Positive correlation means as the x values go up, the y values go up. Being that it's 1, it means that our data values are right on our regression line. An R of 0 would mean that there's no linear relationship. The data values are all spread out. They do not follow the line of best fit. What is the area under the standard normal curve? The area under the standard normal curve is 1, or 100%. The standard normal curve has a mean of 0 and a standard deviation of 1. X bar is the mean of a sample. Mu is the mean of a population. A scatter diagram with a positive R value would have data values that go uphill from left to right. As the x values go up, the y values go up. A negative r value would be a scatter plot where the dots go downhill from left to right. Or as the x values go up, the y values go down. I don't use the equation like this, like the book does. I use the equation that corresponds with the calculator and also corresponds closely to what you learn in beginning algebra. Y equals ax plus b. In this equation, the a value is the slope and the b value is the y-intercept.